Good afternoon. My name is Rajan Cerna, and today I'm going to be presenting my partner and I's mechatronics capstone project. So we chose to do a brownfield conversion of a Lincoln 1000 pizza oven to a reflow oven. I expect this presentation to take anywhere between 15 to 20 minutes. So to start off, I would like to introduce ourselves. Me and my partner Ronald, we are two students from Clover Park Technical College that are both in the mechatronic engineering program. We've worked alongside each other on projects ranging from electrical circuits to fluid systems and other manufacturing skills. Our capstone we chose uh, is to focus all our skills into one project. So a little content overview, we're going to be going over what we learned in applied mechatronics. That was our first part of this project, and then also the capstone uh, new stuff that we added, such as the Gantt chart and project overview. So the project at hand is a brownfield conversion. We're going to be taking two conveyor pizza ovens and then turning it into a reflow oven to manufacture electronic circuits. The definition of a brownfield conversion is basically taking a legacy equipment and legacy software that performs discrete functions in isolation. In most scenarios, nobody is willing to modify existing well-functioning legacy assets. So the definition of a reflow oven is um, a process in which a solder paste is used to temporarily attach one or thousands of tiny electrical components to their contact pads, after which the entire assembly is subjected to a controlled heat. The solder paste reflows in a molten state, creating permanent solder joints. So the parts, tools, and area we were assigned with. Parts, we were given two Lincoln Electric Pizza Oven Series 1000s, a Siemens 1200, DC motor, AC motor, Dayton speed control, a PLC board, and wires. Tools we had were wrenches, screwdrivers, sanders, various other tools for removing materials such as bolts, nuts, and screws. Our areas were the fifth lab space and the section area for tools and parts, and the applied mech and capstone sections and desks. So to tackle this project, we split up the project into three modules: the heating module, PID module, and PLC module. Now the heating module has all the oven elements such as the fan that blows the hot air and the coils that create the heat. PID module is just the temperature controller and the regulator for the reflow curve, which I'll get to in a little bit. And the PLC module, which will take IOs that we select and use it to control the whole oven. So our design and functionality of the project, we chose to go with a stack design shown in earlier pictures, and we chose this to save space and also help mirror when we do, because we're doing one at a time, so having one on top of the other, it's easier to mirror back to back. So the oven cycle time is going to take approximately 3 to 4 minutes, and it'll go through the reflow curve, which is there's a preheat at 150, and then the flux is activated at 183 C, and then reflow occurs at 220, and then it's cooled at room temperature. Here's the reflow chart that I've been referring to, where it goes from the room temperature and then preheats up to about 150, and then there's a slow increase up to 180, where that's called the soaking zone, and then the reflow peak right here at 210 to 225. That's where the reflow solder paste will happen, and then the cooldown period. So this is our sequential functioning chart, which is to assist us in the PLC programming and creating an I/O list. So from here we have the conveyor load. So we push to start the PLC. So that's one I/O, and then the conveyor will run. There's a sensor, that's another I/O, and then the conveyor will stop and then have a ready light, which we'll have to press to continue. And then we'll have a continue button, which will start the PID. The oven cycle will go through the reflow, and then the conveyor will um, eject the part once the reflow is done. And then once it has reached room temperature again, the oven ready light will go on, saying that we can put another part through. Now here's our Gantt chart that me and Ron created for Capstone. We have I cut out the planning section because we're starting from the operational level and then going straight into tactical. We had to plan our functionality, and then also our PLC plan, and then plan out our IOs. That was all completed in week 1 and 2. And then straight after that, we went to the tactical level of adding any parts that we needed to the bill of materials, creating a new sequential functioning chart, cleaning the oven further, testing AC fan, DC motor, um, having to set up the board and then test the speed controllers. These are all completed. Our last thing that we completed was the PLC programming. And then the deadlines that we had was to create a wiring diagram, the final project presentation, and the Gantt chart, which we all completed by the last day of the quarter. Now here's a wiring diagram of the heating elements that we were going to keep of the oven. So we have the sets of coils and the motor, which will be run through the 3 phases. So we're keeping this the same, and we're not messing around with this. We wanted to keep the oven, which was functional, as intact as we found it as possible, so we don't need to deal with any rewiring. Now here's where we're planning on having all our control units. So we are going to have our PID right here, and then our Dayton speed control, and then our PLC. And then here we have our I/O control panel. We're sticking with the same on-off switch that the oven came with, and then we're implementing a heating on and off button, which will turn on the AC fan and the heating coils. Then we also have a DC motor on and off button, and then we're also going to have a directional switch for the DC motor, and then we're going to have our speed controller on and off button, and then on the other side, we're going to have the actual speed control. So we could implement another IO right here for the actual dial of the speed control, but this is just an on and off button. And then we're going to have a e-stop right there. So here we have our wiring diagram. This section right here is all just PLC. Is all just PLC wiring. And then here we have our 3 phases going into our first contactor. And then that first contactor, T1, goes straight to the normally open gate on the third contactor. T2 goes to PLC power and also PLC output power. And then T3 goes straight into the first contactor normally open gate, which will control the speed control. So the way that we have it set up is that the relay will be able to switch all 3 of the relay coils. The first output will turn on the AC motor, so it'll close this gate when we send power through A1. And then second relay output will control the DC motor, so it'll turn on the DC motor. And then the third one will turn on the DC motor speed controller. And then all these coils are linked up to neutral. So there's our wiring diagram. And then here's a diagram of what our PLC programming looks like. We have normally open buttons that count, so it's basically a toggle switch for all three outputs. So we only use one button to toggle it on and off. There we go. So our project overview coming at the end of Capstone. The learning outcomes that we got were how to research and find equipment needed for projects. We learned ways to integrate modern controls to old technology. We learned group orientation, uh, communication skills, so who's gonna do what, who's gonna do it when, and all that. And then organizing large projects. So going back to the Gantt chart, like how we planned it out from the get-go, how we're gonna uh, finish the project. And then during the 10 weeks, we ran into some complications. Some of the big ones were we were waiting for parts to come in, so we couldn't actually focus on how we were gonna uh, program the oven. It was more how we were gonna create a mock-up of how the oven is gonna work. And then wiring an e-stop and programming it, we ran into an issue where the PLC wasn't correctly configured with the safety parameters. So we were already on a time crunch, and then we had the COVID-19 incident where we lost even more time while we were learning and trying to figure out how to create that safety protocols to create a e-stop. But we made do by wiring a manual e-stop, a hardwired e-stop, and then simulating the mock-up project. We couldn't finish that because we couldn't get the PLC to work with the e-stop and programming. We had low time, and then the sudden, I guess, quarantining of the school, and then time constraints that goes back to the COVID-19 incidents, and then also purchasing department. We were constantly getting screwed by them because they just wouldn't uh, accept our order, and that goes back to parts waiting to come in. We couldn't work on the actual oven, so we had to create a mock-up, which was confusing because we had the mock-up program and wiring diagram, and then the actual oven programming and diagram. So that created another issue there. So after all this, we came up with a plan for how it can be continued. So once the parts are purchased and available for integration, a new group of students can go ahead and install it. We've created plenty of documentation for where and how to install it all. And then they're going to retrofit with new parts available. Uh, they're going to have to program the Siemens 1200 for the actual oven operation, not the mock-up that we created. And then continue to run, test the operations, test for any hardware incompatibilities and stuff like that. So yeah, that concludes my presentation. Thank you for your time and have a good day.